Hey Crocker, let's talk about seafloor spreading. It's amazing how world wars and just the technology ends up benefiting just different aspects of science. And this is no different with the case of World War II. Warships carried echo sounders and airplanes carried magnetometers. Their goals were the same: to find enemy submarines. However, what they ended up finding instead, they found submarines, but they also found out the mechanism that drives the moving of the continents and continental drift. Uh, Old warships carried echo sounders. Echo sounders, a lot like a fish finder. If you're ever lucky enough to go fishing, it's a sound wave that creates a picture of the seafloor below it. Nowadays, we have three-dimensional echo sounders, but in the old days, they just had like one ping that come down and bounce back up to get an idea what the seafloor looked like uh, below the ocean. Right now, a geologist from that was working on a boat in World War II conducted sonar mapping of the seafloor. His name was Harry Hess, and he came up with a hypothesis or a theory that states that the seafloor spreading is what's driving the moving of the continents, and a theory that ultimately became known as plate tectonic theory. We'll learn about plate tectonic theory next week. Now, the evidence that drove seafloor spreading really starts off with Harry Hess. It is an observation. The mere fact is that the seafloor is not flat as people envision. People used to think that the seafloor would come like a bowl, right? Really kind of like that. But it turns out that's not what the seafloor is like at all. Instead, there's a long mountain chain, also called as a ridge, right? And there's this ridge line that runs right down the Atlantic Ocean, but there's a lot of other places as well. Now, Harry Hess was out in the Pacific Ocean. There's the Atlantic Ocean. Now, it turns out there's a mid-ocean ridge, a long chain of mountains that rise high above the sea floor. You wouldn't know this if you're on top of it, right? Unless you actually happen to be in Iceland, where that ridge actually pops out and actually becomes land right there. That's where Iceland is. There's also a rift zone. All right, so if you have a mountain or ridge, at the top of the ridge, it stops and it kind of turns out to be a little V valley. All right, little V valley. So the ridges, so you have a ridge and then a rift. Have you ever had a rift with a friend, kind of breaking apart? I hope not. All right. So anyway, that's a rift. So there's a rift zone, and that rift zone continues throughout the entire ridge line. All right. So that whole mountain range has a rift zone, as though it's actually splitting apart. And there are deep sea trenches. A trench, unlike a trench, is the opposite of a mountain. A trench is a depression in the ground. Right. So a trench is like basically it gets to be very, very deep part of the ocean. In fact, one of them they found out is like 8 miles deep below the ocean floor, the Marianas Trench out in the Pacific Ocean. There's deep sea trenches. Some of those trenches are by the continents, some are out in the oceans. Here's a quick animate for this very thing. Notice that the boat carries the simple sonar. This is just a single ping, and it basically times how long it takes, the speed of sound takes for that beam to come back. Echolocation. Some organisms like bats do this naturally. All right. Nowadays, they don't send one beam, they send several beams. Now, this appears to be 3D, but in fact, they actually can send up to, I guess, 426 different beams at once, all sorts of ways. Therefore, they can get a really large reading of what the seafloors look like. So we have a pretty good understanding of what the seafloor looks like based on this type of tool, which is sonar mapping. Now, the second piece of evidence comes from magnetic polarity of the seafloor. And turns out that the evidence is that if we got this mid-Atlantic ridge, which is this line here represents, this mid-Atlantic ridge, as time goes by, what happens is that the seafloor that surrounds it has different magnetic polarity. Pretty big surprise. No one ever would have expected it, and it has to do with polar reversals of the Earth. I have a video on as an accompanying assignment. I encourage you to watch that video. You'll have a better understanding of this concept of magnetic polarity, the sea floor changing. But anyway, there's stripes, basically stripes of different magnetic polarities of the ocean seafloor. Now remember, the seafloor is made of an igneous rock called basalt, and that has tiny magnetite crystals that line up with Earth's magnetic field at the time of its formation. So it turns out that the magnetic floor, that the seafloor has these stripes, and it has them symmetrical patterns, and therefore this will be what is called normal polarity. Normal polarity. This would be reverse polarity. But notice the symmetry. What you see on one side, you see on the other side. There's a good. I put a video on for you guys to check out if you want to see that later on magnetic stripes. Um, Feel free to check that out if you can. Evidence three is age of the seafloor rocks. And that tells us that, as you would imagine, that this conveyor belt is truly actually occurring, then you would expect the seafloor to be youngest over here where the rock is forming, and oldest as it moves away from the ridge line. All right, so another piece of evidence number three, is the age of the seafloor rocks. And it turns out that not only that, the oldest seafloor rock, which is right over here, the oldest seafloor rock is only 180 million years old when compared to the continental crust is far older, and in some cases 4 billion years old. So Harry Hess made a claim, and Harry Hess's claim says this new seafloor is made at mid-ocean ridges. The continents are pushed away. So Harry Hess takes this evidence, the evidence of, let's see, the magnetic polarity of the continents, the mid-ocean ridges, all right, and the rift valleys, and the age of the seafloor rocks, which is all done from radiometric dating. And they claim that the ocean floor's movement begins at the mid-ocean ridge, and that ocean floors move like conveyor belts, carrying the continents along with them. All right, so this is Harry Hess's claim based on the evidence we've talked about. Here's one more animated that Harry Hess wasn't able to use during his time, 200 million years ago. And you can see, oh, we had a magnetic reversal 180 million years ago. And whoop, 155 million years ago, reversal. 135 million years ago, reversal. And remember, the dinosaurs died, was it 65 million years ago? We're not even to the dinosaurs yet. Dinosaurs died. Okay, now we're at 38, reversal, a few more reversals. How many died? Another reversal. Magnetic reversals. And notice the conveyor belts of the sea floor. Notice how that works out. I don't have to see that again. Well, not long after Wagner's death, scientists found something else out, that the Earth itself has layers, and that the layer that we live on, the crust, that the Earth is not a solid, is not solid. The Earth actually has a liquid mantle and a solid inner core and a liquid outer core. Now, you might be wondering, how do we know that? And it was because of earthquakes. Take a look at this slide when you have a chance. The idea is that earthquake, the properties of the earth, the seismic waves determine, there's little shadow zones, and it basically tells us the mere fact that that these waves are traveling through different states of matter. And that's why we deducted the mere fact of the Earth as a liquid mantle. And it's that convection currents that drive the continents to actually move. So scientists reason that there's convection currents in the mantle. And this is a reasoning, by the way, at this point in time, and that deeper the mantle. So the idea is that the deeper you go, the hotter it gets, and so for that heat rises, and then when it gets near the surface, it cools, and then therefore it sinks, and you get a convection current. Now we're familiar with convection currents. You studied that in the sixth grade, as I'm sure you recall. All right, so there's a convection current that goes on in the mantle. No better way to explain it than this beautiful video with the animation that explains it. Notice over here that the heat comes up from the core. Okay, pushing right here. Here would be your rift. There's your ridge. There's your rift. Okay, and notice the conveyor belt, the motion of the new seafloor, and notice how it gets pulled down. This is called subduction. There would be a trench right in there. That'd be a deep sea trench. Notice the convection currents, the symmetry of the convection currents in circular. All right, going from one end to the other. All right, so this is what we use to show convection. Now, notice here would be a deep sea trench. This is where where two plates converge together. This is a possible outcome when one plate is more dense than the other. All right. Then that plate gets pushed down. Okay, during this process, gets reheated, pops up, and you end up getting volcanoes near trench lines. All right. So this is the way it all works out. Now we're going to learn a lot more about this volcanic arc islands, and next week we'll get the vocabulary all associated with that. Right now, what you really want to focus on is seafloor spreading, and the fact is that that's what's moving the continents. And we'll talk about all the other ramifications for this later. All right. So what happens is a number of scientists put this evidence together. They say mantle convection drives a process called seafloor spreading. New seafloor is continually being created at mid-ocean ridges, and the old seafloor is being destroyed in these deep sea trenches. And this is the mechanism that's moving the continents. And by the way, weatherman, you were right.